Good evening. In the last lecture, I spoke a lot about how to implement heuristic dynamic programming, HDP, in conjunction with adaptive methods to train a model and an action network. And I promised that this week I would talk about how to do better than the least means squared methods which I showed you last week. Last week I talked about dual subroutines and the importance of building up modular systems of code. I really hope that as a result of this course, a lot of you will be able to work together in building an integrated software package which gives users the ability to access methods like HDP with different options, combined with many ways to come up with a model. It could be least squares adaptation, but there are many other places where we can get models of plants that we want to control. So today I'm just focusing on the critic part of it, the HDP part of it, and I'll be talking about how we can do better than the LMS which I showed you before. Now, as a practical matter, most of the people using these methods are using LMS kinds of methods to adapt a critic. So everything I said before is very much state-of-the-art, and we need to integrate that state-of-the-art capability into more user-oriented systems. I remember many years ago I used to use a package called SAS, S-A-S, out of North Carolina, which integrates many capabilities from statistics together so that people can combine them and use them. I even wrote a paper suggesting that maybe we could put these kind of capabilities into a package like SAS to integrate together and give users many choices. That's part of the background to what I'm going to talk about today. I'm going to start out with a review. 1.5 slides will be review from last time. Heuristic dynamic programming is the general method which trains the weights in a critic network as I showed on this slide, as I defined it in the Handbook of Intelligent Control many years ago. And the basic idea is that at the current time period, or for a database of examples, we look at the outputs of the critic at time t, and then we define a target of what we want the output of the critic to be, which is the critic estimate of the next time period plus the utility function. And we try to adapt the weights here to match the target here. And I showed you the equations to do it with LMS. But if you want to build modular code, the real idea is call a general supervised learning subroutine, which could implement LMS calculations, or it could implement some other way to adapt the weights to reach that target. And the question is there a better way? And basically the answer is that there is a better way. The present state of the art that people are using in RLADP has been very successful across a lot of applications, but it's possible to do better. So basically today I'm going to be talking about a research direction. And if you're not interested in research directions, well, you can skip on to the next lecture. But for a complete understanding of ADP, it's important to understand that we can do better in speeding up HDP and the other methods for training critics. Okay? So today I'm going to be talking about the research challenge of how to do better than least means squared adaptation in using HDP. And the basic point is that there are some principles we can borrow from statistics and supervised learning. Now, when I was putting together this lecture, I was thinking, gee, I could speak for hours on the basic principles of statistics and supervised learning that could be used here. But I'm not going to do that because I want to stay on course, so I'm just going to extract a few of the key principles which we have learned from supervised learning in the neural network field and from statistics. Okay? So let me first review a little bit more. In pure least mean squares adaptation, with HDP, on each iteration we adapt the weights simply by multiplying a learning rate by the derivative with respect to the weights of square error. Now there's some people who ask, why square error? Why not cube error? Well, there's a big long literature in statistics, has to do with the normal distribution. There are many reasons why square error is almost always perfectly reasonable when we're dealing with continuous variables like J star. J star is a continuous variable. We're not in the realm of binary logic here. J is a continuous variable. So this formula is generally reasonable. And again, we have a choice when we implement it. We could apply it to one example of x at a time, or we could have a database of x of t and the corresponding targets and adapt the weights in order to make the critic predict the targets all across the weights. And some people train neural networks or other kinds of critics in a batch mode, working through a database. Other people do it one observation at a time. Those are both reasonable ways to go. There are trade-offs between those methods. When you only have, let's say, 100 data points, a lot of people say it's better to do it in a batch because then you don't have to worry about thrashing around from the needs of one example to the needs of another. But if you have 1,000 examples, you might as well do it one iteration at a time, especially if they're widely distributed. But those are just rules of thumb. Either way is mathematically fine. Now, this is a special case of supervised learning. We have a target, we know what we want the output of the critic to be, and we're adapting the weights to meet the target, and the question is, are there better methods of supervised learning? Now, it turns out supervised learning is one of the very big areas that people have done research in and applications in the neural network field. Way back in 1990, I remember people would give tutorials on the whole of the neural network field. And they would start out by saying, we have methods to address 3 critical tasks. One is reinforcement learning, which we've already heard about. Another one is something called unsupervised learning, which is a little bit fuzzy, because it's not always clear what are they trying to learn. And then there is supervised learning. And supervised learning is probably where the most applications came in the real world, certainly in the early days before RLADP started coming on strong. So in supervised learning, a supervised learning method is a general method which allows you to adapt the weights of a function so that the actual value gets closer to a desired value. Now if you look closely at this slide, you'll see I said f or underbar f. Underbar f, I'm talking about a vector. And oftentimes we'll have a neural network that has multiple outputs, so its outputs form a vector. And usually when people talk about supervised learning, they talk about the general case where there are multiple outputs, and for each output there's a desired value or a target. But in HDP we're dealing with a special case where there is only one value that's a target. J star is one number, it's not a vector. So we're trying to train a critic to predict the target for one number, and so it's not really a vector in this special case. But in any case, that's what a supervised learning method is. So as I said, simple least mean squared is not the most powerful supervised learning system. There's been a whole lot of research, particularly in the neural network field, drawing on statistics to try to come up with more powerful supervised learning systems. And there is software off the shelf that people use in areas like prediction and classification, which will do a better job. And basically what I'm talking about are things that are called tuned versions of backpropagation. I'm not talking about some of the other methods for machine learning like discriminant analysis that aren't really relevant to us here. Okay? Let me also emphasize, supervised learning systems are just a special case of a more general task I've mentioned called cognitive prediction. In supervised learning you have inputs now, desired outputs now, but in the real world when we're training a model we really have a time series. So we have multiple inputs over time predicting a time series. That more general problem I've called cognitive prediction. So if you want to know more about the mathematics of cognitive prediction, if you want to learn more about supervised learning than what I'm going to talk about today, there is a web page, www.werbos.com/erdos, erdos.pdf, and that has words as well as slides and goes into great detail on the whole big field of cognitive prediction, which could be a course in itself, as complicated as this course. So now I'm going to get to the point, and I'm just going to list a variety of ways where we could do better than LMS in training a critic. And again, people aren't really doing it, but these are useful techniques if you want to do better, if you think HTP is going too slowly for you, if there's a problem. It's important to understand that there is a big state-of-the-art on how to do better than LMS. So, let me go through what are the most important methods. These are important for all supervised learning and for all prediction, for learning models as well. And by the way, these are not just for HTP, they are relevant to the other critic methods I'm going to talk about next week. Next week I'm going to be talking about dual-heuristic programming, which is much more powerful than HTP. But if you understand HTP well, DHP is just one more add-on to the basic principles you can learn from HTP. The first important thing that people do in supervised learning is instead of just minimizing square error, they minimize square error plus a penalty function, which is a function of the weights. The most common penalty function is just a constant times the size of the weights, the sum of the squared weights. In the Handbook of Intelligent Control, Chapter 10, I do talk about some alternative penalty functions, and really the research really hasn't reached equilibrium on what is the best penalty function to use. A lot of people started moving on to other topics. There is room for basic research on how to do better than square weights as a penalty function. This is an extremely important idea. The basic idea is, instead of just minimizing error, we want to prevent the weights from being too large. This is really important in dealing with a problem statisticians call heteroscedasticity, multicollinearity. Actually, it's multicollinearity. The basic idea is, if you don't have enough data, if you have a lot of weights in your model, if you have too many weights in your model, and you don't have enough data, you may not come up with an accurate estimate of the weights. If you use a statistics package, they will usually output a number called standard error associated with each weight. And that gives you an idea of the margin of error for that weight. In fact, in standard textbooks on nonlinear regression, they give you an idea of how to estimate the standard error for any nonlinear function, and that can be used with neural networks. So with neural network packages, it's possible to write a supervised learning module which outputs a standard error for the weights. It gives you an idea of how uncertain you are. It often happens in statistics and in neural nets, there are just too many weights. And then you face a choice. What do you do? If you have prior knowledge about the structure of the problem, you could just get rid of some weights based on your knowledge. But if you don't, it's very useful to have a way that the statistics can decide how to prevent the errors you get in prediction, which result from high standard errors. And there's a standard method in statistics which is called ridge regression. There's a great classic paper by a guy named Brad Efron from Stanford University way back in the 70s. It was called Empirical Bayes. And basically what he pointed out was all you do is add kw squared to your error function, minimize that, and you get a much more robust estimate of the weights. You get a much better model than you would if you didn't put in that penalty function. Another reason why we believe in penalty functions has to do with the fundamental nature of learning. There are a lot of people who study machine learning and artificial intelligence who learned about something that they call Solomonoff priors. And actually, my Erdos paper talks a little bit more about the history of it and what these things do. But the quick summary is, humans would not be able to learn anything from experience if our learning did not reflect a basic principle called Occams Razor. The principle that a simpler model is more likely to be true than a complex model if both of them fit the data equally well. So if two different systems of weights and connections have the same square error, but one is simpler, the simpler one is more likely to be true and also more likely to give good predictions. It's not just the probability of truth that matters, it's the probability that your predictions will be erroneous. So it turns out that when we get to the world of continuous variables, these Solomonoff priors they talk about in the digital world don't really tell us how to deal with continuous variables. But with continuous variables, this kind of penalty function has the same kind of value. It's really fundamental to learning in the face of complexity. And so penalty functions are very important. There are plenty of working penalty functions out there in supervised learning packages, in neural network packages. There's lots of work on penalty functions you can use. Chapter 10 of the Handbook of Intelligent Control gives some examples of penalty functions. These are extremely important when there are a lot of weights. With the generalized MLP, there are lots and lots of weights. They give you a lot more flexibility than you would have with a simpler type of neural net with fewer connections. But then you need to cope with those weights, and one way to do it is by putting a penalty function in to reduce the weight vector, to reduce the standard errors. Closely related to the penalty function, also important in supervised learning in statistics, is the notion of pruning. And the basic idea is, if a weight is very small, just set it to 0. Again, there's a huge literature on pruning, not only in neural networks, but in statistics. It goes all the way back to a really seminal journal issue, way back in the 1970s, in the Journal of American Statistical Association, where they did empirical studies of 57 ways of trying to deal with multicollinearity, with linear models. And what they found out was you get the best results by combining ridge regression with the right factor k with a certain amount of pruning. And again, pruning is also discussed in the Handbook of Intelligent Control, but there are lots and lots of programs out there which do pruning for backpropagation in the real world. All of that kind of stuff can be applied here. A third important method that can be used in training critics is what I call an adaptive learning rate. That mu, the learning rate in the formula, doesn't have to be a constant. Now there are some people who are doing ADP who try to determine the learning rate by a fixed formula a priori. Some kind of strange thing like, 1 over the cube root of t, the time or the number of the iteration. And using those kind of ad hoc formulas, you can prove some theorems. So this is useful, but that doesn't give you the fastest convergence. In the neural network field, we have found ways to adapt learning rates which are a little more rational, based on some concept of optimality of the learning rate. In the Handbook of Intelligent Control, Chapter 3, up on the web, the equations are there for a simple thing I call the adaptive learning rate. In the old days, I did a whole lot of implementations of backpropagation for things like large-scale energy models. And what I found out was that simple steepest descent would often oscillate a lot and be slow, but when I used this very simple adaptive learning rate algorithm, it would allow things to converge to 12 decimal places in 40 iterations. Those are real numbers from a paper I published on the official model of natural gas that I developed for the Energy Information Administration years ago. That's published in IEEE Transactions, Systems Managed Cybernetics. So the bottom line is this adaptive learning rate works very well for ordinary multi-layer perceptrons. It leads to very rapid convergence, at least in batch learning. With really complex neural nets, it's not powerful enough. But for ordinary multi-layer perceptrons, it works quite well. There are also lots of packages out there, neural network packages, which use other methods similar in flavor to the adaptive learning rate. There's one called RPROP, which is one of the methods in the Stuttgart Neural Network package, SNNS, which you can get on the web. There is also a package called Neurodimensions, which you can use for free on the web, even though you don't get the whole package for free. And there are a whole lot of packages out there. People who use backpropagation with neural nets in a naive way often take thousands of iterations to get anywhere. But with just reasonable little tricks, things go much, much faster. And those tricks are out there in the open literature. So that's one set of things that you can do. There are more things you can do. When we talk about adapting in proportion to the derivatives, we're really talking about a classic method from operations research called gradient descent or steepest descent. And any old textbook on function optimization from operations research or numerical analysis will have a section on steepest descent. There are many people who will tell you steepest descent is impossibly slow. And it turns out that's somewhat misleading. They say it's impossibly slow because it's only kind of an exponential reduction in error. But if you cut your error in half every 3 iterations, it only takes like 30 iterations to cut it by a factor of 1,000. And that's my experience. Steepest descent is slow, typically, when the variables are not well scaled. So the program is thrashing around working on one of the 40 parameters you're trying to estimate while not improving on the others. And that's why having adaptive learning rates can be useful, because adaptive learning rates can learn to scale different weights differently, and you avoid that kind of thrashing. And when they all move down together, things are fast enough. But another way to make things move quickly is to just scale the variables so that the amount of variation you need is about the same on the different variables. Simply scaling the variables turns out to be very important in speeding up steepest descent all across the board, not just in neural networks but in other applications. Now that's not so important to HDP, because in HDP there's only one variable, the J star. Adaptive learning rates can be useful in HDP, but there's really only one variable here. But when we move on to dual heuristic programming, everything I've said so far is related there, and since they're different variables in dual heuristic programming, it might help to scale. So this is kind of a placeholder for more advanced stuff. But there are more methods you can use. In HDP, and each iteration, we're trying to adapt the weights to minimize the square error in predicting the target. When you think about it, this is a problem in one-stage function minimization. We know what the error function is we're trying to minimize, so this is not a stochastic problem. It's a one-stage deterministic problem. And you remember from the beginning of the course, there has been a whole lot of work in operations research to come up with good methods for minimizing a function for a single-stage optimization problem. We can apply those methods here to supervised learning or to HDP. Now, a lot of the methods from operations research are too expensive. Good old LMS, the calculations are only on the order of n in cost. If they're n state variables, we have a nice sparse neural network, the cost is only on the order of kn. So even if we need a lot of iterations, each iteration is pretty cheap. Some of the methods from operations research, like Newton's method, are on the order of n cubed. And as n gets to be large, that's not a good way of training a very large system, because n cubed is too expensive. But operations research has also worried about computational cost. And there are excellent methods developed in operations research to try to solve this kind of optimization problem as accurately as possible within a cost constraint. Those are important to us too. We can use them with neural networks, for example. Some people think the brain may be implementing some of those kinds of methods. There's pretty sophisticated stuff going on in the brain. As long as it's parallel, the brain might be implementing it. Within the field of operations research, there are many methods which have order of n cost, just like the neural network methods. The most important ones for practical use today are two methods. One I would call the Shano conjugate gradient method. And there's a guy named Dave Shano at Rutgers. Boy, I hope, yeah, he's still active last I checked. He is a great classic figure. He has achieved breakthroughs through clear, concrete thinking that are just unbelievable. He's done a lot of work in operations research of enormous practical importance to us and to many kinds of optimization. So Shano developed an advanced form of conjugate gradient method, much more advanced than the simple versions you'll find in the usual computer science handbooks of algorithms. But Shano himself was very happy when he could say, there's another method more powerful than my method. I'm very happy about this guy Nosedal. The more powerful method, the most powerful method we have today, which is of order n, is called LBFGS, where S stands for Shano. It's basically a simplified, approximate form of a method Shano developed for the more expensive case, order of n squared. If you're willing to pay an n squared cost and get better results on each iteration, the standard methods in operations research are called quasi-Newton methods. And for ordinary optimization, the best quasi-Newton method is indeed this Broyden-Fletcher-Powell BFPS method. But HDP is different. Normal optimization, you have a fixed target. You don't have a moving target. But we have a moving target. The targets change. We adapt the weights and then we have new targets. That's a little different. So in operations research, they take advantage of the symmetry of the Hessian because they know they're doing a fixed optimization problem. We can't really do that. So in our case, there are older methods, also somewhat powerful from operations research, something called the Broyden method, which doesn't take advantage of symmetry, and so it may work better in our case. There's another order of n squared method called extended common filter learning. And some people look at that and say, oh, you're using common filtering to estimate the state of a partially observed system. No, we're not. This is a way of using the mathematics from control theory, from common filtering, but we use it for learning. There are basically two groups I know that have had the most success using EKF learning, which is order of n squared. And one of them is Ford Motor, which has used it in numerous real-world applications, running on the road today, critical to the company. And another important paper is by Elin, Cosma, and myself in Transactions on Neural Networks, where we used it to train a complex type of neural net, complex enough that the ordinary adaptive learning rate didn't work very well. I mentioned with really complex recurrent types of networks, adaptive learning rates can start to slow down, and in our experience, the EKF learning could converge much faster for the problems we studied. It's an interesting question. Does our EKF learning method go faster than the Broyden method would on the same problem? Nobody knows. That's something we have to do research on, and it's kind of interesting. When I mention this moving target problem, I should mention there's much more mathematical detail available on that for people who want to follow up on accelerating HDP. I have a paper way back in 1990 in the journal Neural Networks called HDP as a Reinforcement Learning Method, where it describes why we basically don't have a symmetric matrix for our optimization problem here. And so we need to use slightly different operations research methods. Now, with ordinary supervised learning, there's another way to accelerate things by use of memory. In fact, memory work can work out a lot like ridge regression with ordinary supervised learning. It's very critical. If you want to build a brain-like system to do supervised learning, there are certain memory capabilities you need to inject. I call them syncretism. I talked about them a lot in that ERDOS webpage. But with HDP, it doesn't work as well. Because every time you adapt the weights, you have a different target. So your memory of the past becomes invalid more quickly than it would with a normal prediction problem. And finally, the last thing I want to talk about here in the research is that I believe it's possible to do something I would call modulated backpropagation. I talk about that just a little bit in my PhD thesis. It seems to me that when we propagate derivatives back, as part of the propagation of derivatives, we can put in damping or amplification factors, not just on the learning rates at the end of the process, but in between in the middle of the neural networks. And I have a strong feeling that the fastest training of any neural network will involve a better use of this concept of modulated backpropagation. This is another opportunity for research in the future. So that pretty much concludes the research for the future. I am going to go briefly back to the bigger picture to put all of this in context again. Next week I will talk about DHP, which is more powerful than HDP, at least when you have continuous variables. But I want to talk again about the big picture. Remember I talked about levels of intelligence. And in the beginning of the class, I talked about different types of stochastic process. To understand RLADP and even HDP, it's really important to remember HDP and J-star kind of critics can be applied to any of the three kinds of stochastic processes I talked about in the beginning of this course. With finite state systems, you basically have Markov chains. When you have an optimal decision-making or learning system for finite state machines, I should call that finite state intelligence. And a lot of the work out there on ADP is just limited to that case. And they hope that it would generalize to the vector case. Finite state mathematics can be very useful in giving us insights, but it's not powerful enough. Finite state intelligence is basically addressing Turing machines. Today I've mostly talked about vectors, sets of continuous variable x or continuous variable r forming a vector, and I've been talking about critics which are a function of a vector, and I've stressed how to train them. So for vector intelligence, we need penalty functions, for example, which are more general and more powerful than the simple concepts of Solomonoff priors people talk about up here in the finite state case. We need a more general concept. It's kind of interesting, Robert Kozma has mentioned, there's a concept of super Turing capability. Hava Siegelman has published papers developing the mathematics, showing how you get super Turing capability basically in this case. So vector intelligence, we're really talking about optimizing what you get with super Turing intelligence where it is continuous variables. And this is more general and it requires new tools, and this is what we've been applying in engineering. But ultimately, as part of getting to the level of intelligence you see in a mouse brain, we need a lot of research now in going a step beyond. The big needs we have for research today are for the best possible vector intelligence, including the kind of things I talked about today. But we also need people who are stronger abstract thinkers, willing to go a little further, into this realm I call spatial intelligence, where the stochastic process is something like a Markov random field, where you have complex images, and in that domain you need something like penalty functions which address the concept of symmetry in space. So there are new principles reflected in new priors which enter into what you need to minimize with a critic. You could still use HDP or modified HDP. That kind of training is still legitimate, but what you minimize is affected by the fact that instead of inputting a vector, you're inputting a whole matrix. Leon Chua has talked about a higher level of intelligence you can get to here. You might call it super Turing intelligence. I don't think Chua has proven as much as Sigelman has, but he has proven things which he claims that super Turing can do as well as quantum computing. It's a whole order of intelligence beyond that. And I claim that to replicate the intelligence in a mouse, you have to achieve this spatial intelligence plus a couple of extra capabilities. So next week I'm going to move back to something more mundane, DHP, which is the same framework, the same methods, but a different way of generating the target. And instead of J, it's lambda. Thank you.